Good evening, sir.
Not joining. I think we'll start, no problem. Let me make you the co-host. Nanjay can start, no problem.
Sir?
You can start. Now
Okay,
step
okay.
in three.
Okay, sir.
Let them join later, so the recording will be uploaded. You can start.
Let me share.
You handle the session for the next 30 minutes. I will come back.
Oh, okay, sir. No problem. Is it visible?
Yes, yes.
Yes, sir.
Okay, okay. So, good evening, everybody. So, today, what we'll discuss another important embedding or text representation. Okay. So, till now we have discussed how to vectorize different documents. When I say document can be any sentence. If it is the database contains sentence, so it is a sentence. If the database contains paragraph, so it can be paragraph. So generally, whatever vectorization technique we have discussed, all are based on documents like bag of words, TF-IDF, bag of n-grams. So all of them, what they are doing, they are not creating vector for every word. Rather, they are creating a vector for the whole sentence or whole document. Okay. So today, what we will do, we will discuss how to vectorize words and also see how why they are very useful. Also, we have discussed one technique bit for vectorization of words. Also, today we will see again that, and specifically we will discuss static embeddings, means the vectorization of words which are static. Okay, that means once the vectorization is done, means it is fixed, and you can use that vector for these specific words or all these words in further processing. Okay, and when we'll do this vectorization, we'll try to find out some aspect of word meaning, need to capture some aspect of word meaning, and we have already seen how to capture this. Today we'll discuss a little bit more on that. But the static embedding is the second step when the development process starts. First, this is the basic BOW, TF-IDF, and bag of n-grams. After that, what happens? The static word embedding for words that have developed, and also it has very quite successful. Also, we'll see one example today in hands-on demo why it is successful. After that, but nowadays the NLP world has moved to more contextualized embeddings, which will cover later. Okay. So please mute. Please mute. Mute, please. Who is talking? Please mute. Okay. So let's start from basic word embedding, which already we have discussed. That is called your one-hot encoding. So it is a word embedding techniques. Try to understand the BOW, TF-IDF, bag of n-gram. These representations or these techniques are used to represent a document. Here, we are discussing about how the words will be represented, not the document or the sentence. And one such word embedding already we have discussed. Again, I am discussing that. That is called one-hot encoding. So it is very simple, and it is a hand engineered representation. So what it has? Let's say we have a vocabulary, because when you want to create a one-hot vector for words, what you need to create a vocabulary set. Okay, so let's say this is my vocabulary. How many words are there? 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 words. So using these 8 words, I want to vectorize for every word. So one hot encoding says that the size of each vector for every word is the size of the vocabulary. So here we have 8 vocabularies. So every word will have size 8. So it is a 8. The shape of the vector is 8. So now you see. So here the length of the vector is mod v, that is number of words present. For example, if I want to create a vector for cat, so you see cat is in third position. This is the index. So here 0 0, third position is 1, rest all are 0. And the number of positions present in each vector is the length of the vocabulary. So here the vocabulary has 8, so it has 8 dimensional vector. Okay. Similarly, feline is in fifth position. So here it is 0 0 0, fifth position is 1, and the rest all are 0. So we know that this is a very simple word representation, which we call it as one hot embedding or encoding. So but what is the problem with one hot encoding? Try to understand. So let's see, that already we have discussed. Feline is one, but one problem with this is that the matrix or the vector what we have created is sparse. Imagine a situation where your corpus has a 20,000 vocabulary. Means the vocabulary will be obtained from the corpus. Already we have discussed that. So if a corpus has a 20,000 word vocabulary, then every word will be represented by a 20,000 vector. The length of each vector will be 20,000. And among these 20,000 positions, only one position will be 1. Rest all positions will be 0. Okay, that means the vector is sparse. This is number one problem. Okay, then another problem is that it cannot capture any meaning or relationship between the words, because we know that sometimes words has their meaning, and how to capture that. Now if a word is similar to another word, if we can capture that also, somehow indirectly we are capturing the meaning. So now you see, in one hot encoding, no such thing is available where the similarity or the meaning can be represented by these vectors. For example, you see swim, swimming. So these two words are quite similar, or the meaning is the same. Cat, feline, that is also same. Boss, car, road, they have similarity. But if you use these vectors, you take any vector pair, and if you do a dot product, it will give you 0. Why dot product? Because we know that to find out the similarity between two vectors, so we are using cosine similarity. It is nothing but the dot product. Okay, so we know that every, let's say swim is a word and swimming is another word. In swim, let's say swim position in the vocabulary is fifth, swimming position is, let's say, sixth. So here fifth position will be 1, rest all are 0. And for swimming, sixth position will be 1, rest all are 0. If you do a dot product, so fifth position of this multiplied by fifth position of swimming. So here in swim, fifth position is 1, swimming fifth position is 0, so it will be 0. Similarly, sixth position of swim is 0, sixth position of swimming is 1, so when you multiply, it will be 0. That means two vector, when you do a dot product, it will give you 0. That means there is no similarity. So in this way, we can say that the one hot vector do not have the capacity to capture the meaning, as it cannot capture the meaning when we have similar words and we try to find out the similarity score between these words, it is giving us 0. Okay, so this is the problem. So what will be nicer? It would be nice to have a short and dense representation, as well as this representation should capture meaning of the word. Till now, the representation is very sparse, long and sparse, and it cannot capture the meaning. And now we need a vector representation of words which will be short and dense. Dense means all values will be there, and some position may be 0, but not all. And it can capture some kind of meaning from that word. Okay, and one such representation we call it as, this kind of representation we call it as embedding. What is embedding? So embedding is nothing but representing a discrete item as a vector of real numbers. Discrete item means, here discrete item can be anything. Discrete item can be a word in a sentence. Discrete item can be a movie. Discrete item can be a book, can be a people. So you can, if you use this concept, you can represent anything anything as a embedding, and we call this as embedding. For example, it is nothing but collection of discrete items like movies, books, people, etc. It can be word also. Okay, let's take one example, it will be clear. Let's say I have different movies. I want to create a embedding, means representation, dense representation for each movie. And we have decided that to create a five-dimensional vector for each movie. Okay, now when I say that I have to create a five-dimensional vector, then question is for each position of the five-dimensional vector, what will we need? So it says that if it is embedding, you need to put some real numbers. But for what features? What kind of feature these real numbers will capture? Let's say it can capture the genre of the movies. What is action, comedy, drama, horror, romance. So these are the five genre for the movie. So every movie will have some action. So what is the amount of action that movie has, that will be represented by the action. How much comedy is there? So that will be represented by the comedy matrix, comedy value. Drama, horror, and similarly romance. So these are the five things you can use to represent a movie. Okay, what does it mean? It means action means how much actionness is there in that movie. It can be 0 to 1, or it can be any real number. It can be minus 500 to 500 also. That there is no means it is not limited. You can put any real number. Similarly, for let's say the movie is Godfather, the Godfather. So if I want to represent the Godfather as a five length of five vector, then the action is zero point 0.5, means 50%. It's not actually percentage. 0.5 is the actionness, zero point 0.2 is comedy, zero point 0.9 is drama, zero point 0.3 is horror, zero point 0.2 is romance. So this is the Godfather's representation, and we call this representation of a movie as embedding. Is it okay? Similarly, I can have another, let's say big Lebowski. So here, same five-dimensional vector, and it has 0 0.3, 0 0.8, 0 0.5, 0 0.1, and 0 0.3. Now, if you can find out a similarity score between them, so that it can give you how much these two movies are similar. If you have a recommendation engine, if you want to create, then you can store these embeddings. Try to understand, it is another problem here. So nowadays you, whatever movie you have watched either in Netflix or in Geo Hotstar, automatically when you come back to this app again, the similar kind of movie is recommending to you. How he knows? So actually what happens, for every movie, generally you can also create such kind of things. You can represent this movie as a embedding, 5 vector, 100 vector, whatever. Every movie is represented like this. Now, once you open a movie and watch it, then the embedding of that movie is selected. So it will, in next time when you will come back, what it will do, it will find out the similarity of this embedding with other embeddings present for other movies, and the movie which are most close to the movie what you have watched by the similarity score, these movie will be recommended and will be shown on your screen. So that can also be used. Okay, so this is one way. We call this as embedding. Instead of putting whether the movie is present or not, whether the action is present or not, comedy is present or not, instead we are putting some real values. Okay, so movie with the similar attribute will be closer to the together in a vector space. Similarly, if you want to represent a person or people, so you can create a, let's say create a three length of three vector. So here vector size is 3. One represents age, another represents height, another represents weight. So now every person can have these three values. So you can put them in a vector like this. So this is called a collection of people, and they are embedding. And if you want to find out which people are similar, which two people are similar, you can calculate by using these embedding vectors, find out the similarity score using cosine similarity dot product. Then you can get the people which are close to each other. Okay, and if you put them in a vector space, now here this is one position, this vector is represented by this dot, this vector is represented by this dot, and this one is represented here. So this is the called a vector space, and the dot are called the embeddings, and the distance between them will decide whether they are similar or dissimilar. If their distance is very less, they are similar. If they are far apart, then we call it as dissimilar. Okay, but now, so this is the idea. What we will do, instead of using the movie and the concept we have discussed about people, here what we will do, we will take the sentence, find out the word. For every word we want to represent a vector. It can be a 5-dimensional vector, it can be 100-dimensional vector, it can be any. And this vector is not a sparse vector, rather it is a dense vector, and it represents something, some information about the word, so that when two word representation you get, and you can calculate their similarity, and that will show that whether the meaning is captured or not. Okay, so here the goal is meaningful word embedding. So how will do that? Now you need to create the embedding in such a way that if you put them in a vector space, swim, the vector representation of swim or embedding of swim and swimming must be close to each other. Similarly, dog, fat, feline, they must be close to each other. Car, bus, road, they must be close to each other. That means they will capture some kind of relatedness between these words, and that is nothing but the meaning. Is it okay? So now how will do that? So this kind of similarity between swim and swimming, we call it a syntactic similarity. So because the syntax is different. Here swim, it is swimming. And the feline and cat, they are called semantic, meaningfully they are same. Okay. And they are called semantic relatedness, means car, bus, road. So they are semantically related, because car, bus, they are vehicle. But when it is the road is there, that means semantically they are related with each other, because car, bus must be run on a road. Okay, so we need to capture these kind of information in our embedding. We can do that, then that embedding is much richer than the embedding of the one-hot vector. Okay, so let's take a two example. Dog bites man, canine nips human. If you see, these two sentences has same meaning. Meaning is same. But if you want to create a one-hot vector, so they will be totally orthogonal. Means you cannot capture any meaning. Okay. So now if you do the dot product of your bag of word technique or any other technique, you see there will be zero, cosine similarity will be zero. That means, because you see, if you take bag of word, what it will do? So these word are different, these words are different. That's why the representation of this one and this one will be different. So when you do a cosine or dot product, cosine similarity or dot product, it will give you zero. But actually their meaning is same. But this meaning cannot be captured by using BOW or BON, whatever you use for the document representation. So what we'll do, but using word vector would result in a similarity score. If you create, for every word, if you create a vector, then I can create the vector of the sentence and find out the similarity. Okay. So let's put it more clearly, so that your intuition will be clear. Let's say there are four sentences. The puppy ate the slipper. The puppy chased the ball. The dog barked at the door. The dog fetched the stick. Now these four sentences you know. For example, if I give another three sentences, the Wimbledon fetched the slipper. The Wimbledon barked at the ball. The Wimbledon chased the squirrel. Okay, now the question is, what do you mean by omblibu? Because you may not know what is omblibu. But when you see these above four sentences and you try to relate them, then easily you can infer that yes, omblibu can be a dog or a type of pet. Isn't it? So there can be some same kind of a pet or a type of dog. So because why you are saying that? Because you see, this is due to these words, they are called context words. Okay, so context words means the words which are appear along with this puppy dog. Let's say puppy dog are my target. Similarly here Wimbledon my target. So which words are around it? So here slipper, chased, ball, barked, fetched, the same words are here. As these same words are present here, that says that Wimbledon must be similar to dog or puppy. So when this information, if you can capture, that means the representation of Wimbledon is nearly close to dog and puppy. So how will do that? So this is called your distributional hypothesis. That means the words which occur in similar context have similar meaning. So this concept is called a distributional hypothesis. That means if the words are present in similar context, so their meaning will be similar. So here dog is present in barked, the context of dog is barked and fetched, Poppy is chase and slipper. So Wimbledon is fetched, Wimbledon is barked. So there means these words and these words will be similar. So that means they are similar surrounding words. We call them as context word or surrounding words. So we need to capture this information that if the surrounding words are same, that means their representation must be close to each other. In this way, we can capture the relatedness or meaning of the words in my representation. Okay, so how will do that? So there is a good or best, we cannot say best, but it is a good static representation which comes first, that is called word to vec. Means word need to be converted into a vector. So what word to vec will do? It will learn a dense representation which will capture the meaning or here meaning means in terms of relation between different words. Okay, so let's take an example. So this is a what to vec representation for cat, which is a dense vector. Means you see every position of this vector contains some value, some real number. It is not zero. So this is dense, and let's say here it is given as a 300. So this starts here and ends here. So it is a 300 length representation. But the length can vary. It can be up to from 50 to 1000. So these vectors are often called word vectors or distributed representation. Why it is called distributed representation? Because to create this representation, you try to find out the context word, how the context word is distributed with the target word. So that's concept is captured in this embedding or vector. Okay, so this is my, if you put this, so this is my cat. So here this is one value for first dimension, second dimension, third dimension, up to 300th dimension. Now question is what these dimension or what this position will actually refer. Like in movie case, first one is referring action, second one is referring comedy, etc. But here what it refers, that we don't know, but it represents some information about cat. It may be, but we don't know. It may be this information is petness, it is animalness, it is nounness, etc. But these are black box. We don't know what it represents, but it can represent some kind of information for this word within these position of the vectors. Okay. So what matters here is that related words should have vectors which are closer to each other in the d-dimensional space. Here d can be the dimension of the vector. If it is 300, so in a 300 dimensional space, cat and dog must be close to each other because they both are pet. Okay. So to do this, what to make has two different algorithms. Okay, but here the algorithms actually they directly not learn the word embedding. They are used for some dummy problem, but they solve some dummy problem, and after solving we collect their word vectors from these problems. Okay, so what are they? One is called cbow. It is called a continuous bag of words. Another one is called skipgram. So let's see what are the dummy problems for solving, for creating these word to vec. So here cbow is called continuous bag of word. What does it mean? If you have a sentence, let's say this is a sentence is given, learning dense representation that capture word relationship. So the cbow says that let's say my target word is representation, let's say, and what is my context word? Let's say my context length is 2. That means 2 words before it, 2 words after the target word. So it says that if you have the context word vectors, try to find out the vector for the or predict what will be the target word. Means context word will be given and you have to predict what is the target word using some neural network. Okay. Similarly, skipgram is opposite. Skipgram is you have the target word, use the target word as input to the neural network and find out what is the context words. So predict context words based on the target word. This is one dummy problem. And here predict the target word based on the context words. Context word will be given as input to the neural network. You have to predict the target word. So with these two algorithms, they are solving two different problems. One is, or we call them as dummy problem. One is it is trying, first one cbow is trying to solve that given context word, what is the target word, and in skipgram says that given the target word, what is the context word. But we don't need the solution of these two. Rather, during the solution, the weights of these neural network will be collected. These are called the vector representation of these words. And I will show you the most common algorithm, that is called skipgram, and how skipgram is working. If you understand, then SIBA is similar. Okay, so let's see how skipgram is working. So here the we have used a modified version of skipgram, that is called skipgram with negative sampling. Okay, so what is your goal? So we have to create a dummy problem. What is the dummy problem? That maximize similarity or the dot product between words which appear in similar context. So that means a target word will be given. You have to predict the context word in such a way that it will maximize the similarity of these context. Okay, so let's see. For example, what it means? It means as dolphin and whale both are similar. So when you learn this algorithm or when you train this neural network for skipgram, these two vector value will be pushed to each other. They will be closer, and it will minimize similarity between words which are not similar. Like for example, ketchup and well. So you need to before training, let's say ketchup and well are similar to, means very close to each other, but after training they must be different, means the space between or the distance between well and ketchup vector must be bigger. Okay, so in this way we'll try to find out the similarity, or find out the, sorry, the word vectors. Okay, so let's see. Let's say I have a sentence and this is my corpus. In my corpus or in my database, I have only one sentence. What is that? Now I have passes for the Miami Grand Prix this weekend. So this is one sentence in my corpus. So for creating this, the neural network already there. The neural network says that it will first enter the target word and predict the context word. But how will create the data set from this? So from this corpus, I need to create a data set for my dummy problem. So my dummy problem is given the given the target word, what will be my context word, and a neural network is trained on that. Means one neuron, one input will be there, and it will predict some output neurons. Okay, so let's see. So for creating a corpus from this, how we'll do that? Now first we have to identify target word. So let's say because it will start from actually I, so I have just to give you a simple explanation. So I have taken target word as Miami, and I will show you how it can be changed. So here Miami is my target word. Okay, or this is called the input word. So because problem is given the target word, means input will be the target word, predict the context word. What is context? So here let's say I am taking context length or context window as a 2. Context window 2, if I take, that means for the target word, what are the two words before it, what are the two words after it. So these two words for the becomes the context word, and grand prix becomes the context. So now I have four context words: two before the target word, two after the target word. That means the neural network, when it takes the vector of Miami, it will predict the vector for the grand and prix. Okay, so for that first need to create a data set. So here the target word is Miami, and the context words are for the grand and prix. So first what we'll do, these are the output or context words. What I'll do now, once you see, once this target word and for these are the context word. Now if you shift the window, now next target word will become grand, and the Miami will become the context word, prix this will become the context word. Now when you move the slide the window again, so it will, prix will become the target word, Miami grand will become the context word, this weekend will become the context word, like this. So if weekend become my target word, then after there is no word. So only for this it has only two context words, that is prix and this. Okay. Now how to create a corpus? So you see, what is my, I have to create a pair of words, that is called context target pair. So for the Miami is my target word. So what is the context word? For. So for Miami is one pair, the Miami is another pair, grand Miami is another pair, prix Miami is another pair. So these are called positive context target context pairs. Okay, now these are called positive samples. Now, we are using skipgram with negative samples, so what we'll do, we have to create some negative samples, means which are not present. So here, the Miami is my target one. What I need to sample some other random words from the vocabulary of this corpus. So the corpus may have many words. From this word, I have to sample, means randomly select some of the words which are not in the context. Sometimes some context word may come, but generally it is not the context. So mountain Miami is the negative sample. Elephant Miami is another some negative sample. Price Miami is sample negative sample. Prix Miami, you see here also Prix Miami is positive sample. Prix Miami is negative sample in negative sample. That one or two such pairs can available. There is no problem. Okay, if sampled word is in the context window, there is no problem. Okay, now this is called my training set on. So here, what is my training set? If for is given as input, it will predict Miami. If the is given as input, it should predict Miami. If grand is given as input, it should predict Miami. And like this, negative sample is this one. This is positive, this is negative. And here we are creating the data set from the corpus without any human label. So that is directly it is creating, no manual labeling needed. This kind of learning is called self-supervised learning, which your LLM is also doing that. So in LLM or like this, we are not going to create a manual labeling for the data set. Rather, the data set and label will automatically created. That means for Miami, this is positive. Mountain Miami, this is negative. Okay. Now, once the data set is created, what we'll do? Now it is a binary prediction task. That is given two words. Are they likely to occur close to each other in the text or not? Okay, whether they are positive or not. So I will do that. So for that, we need to create two vectors or two matrices. One matrix is called W, another matrix is called C. So W matrix, the size of W matrix is mod V into D, and the size of context matrix is mod V into D. So here mod V is number of words present in the vocabulary, into D is the dimension of each word. Let's say I want that my all vectors should be 300 dimension. So D will be 300. Okay. And this V, number of row, is number of words present in the vocabulary. Okay. So this is called this W is actually representing the target word embedding, and the C representing the context word embedding. Let's say for Miami, whatever for all words when they are in target, what is their embedding? And for all these words when they are in context, what is their embedding? So this W is represent when the word is a target, and the C is represent when the word is in context. Okay. And if a vocabulary and the goal is to create three-dimensional embedding, will be 10,000 into 300, and C also will be 10,000 into 300. Because you see, each word, sometimes it is target, in sometimes it is context. So when the word is in target, what is the okay? And once this is ready, first what we'll do, for initially when there is no embedding, we have to create one word vector for every word in the vocabulary, and this one word vector will be used as input, and after that it will be modified. So here represent each word in the vocabulary as a one word vector like this. Okay, you know how to create a one word vector. Now you for your neural network, first pick a positive sample. Let's say I'm picking Grand and Miami. For each positive sample, when you pick, you have to pick k negative samples. So when I pick first positive sample, there are two words, Grand and Miami. So for Grand, there is a one word vector already represented, and for Miami also there is another one word vector. So for Grand, the one word vector what we got, the C, this is my context matrix, which was initially represented by all are generally means what randomly initialize these vectors. So you just multiply them. This is called your context embedding. Okay, let's say this is my position, because this one position is here, so this one will be multiplied, so it will give only this value, the rest all will be 0. So when you multiply the one word vector of a Grand with the context embedding, because your Grand is context. Okay, so Grand is multiplied with context embedding matrix, and you will get the corresponding vector for the Grand. Similarly, Miami, the one hot vector representation is already there, and there is a target matrix. So when we multiply the target embedding with the Miami, because Miami is a target word, so when we multiply it, so this vector it will give one vector, and that vector is for the Miami. Okay, and we'll get two word embedding vectors, one for positive context word, another one is embedding matrix, embedding vector, or for the target word. Similarly, what you do, you sample k negative samples. Means once you got one positive sample, for one positive sample, select k number of negative samples. K is a hyperparameter, you can choose. Let's say 3. So for this case, let's say 3. So similarly, what you do, as it is a negative sample, so you select mountain, then multiply with the context vector, it will give you C negative 1, and Miami is my target, and you multiply with the W, so it will give you some W. So now you got 3 corresponding vectors here, and here one corresponding pair of corresponding vector for this positive one. Okay, now the vector is there. What you do, now it is a binary prediction task. That means given two words W and C, are they likely to occur close to each other in the text? So this need to be solved. Okay, so how will do that? Now it is a you can do that using that will be done by the neural network, but to specify it in mathematically, what actually is underlying thing means how it is actually solving it. So you see here, probability of positive given two words. One is context positive and the target word. So whether these two words belongs to positive or not, because we are sampled, so it will give you this means sigma C positive and W. And also we have to find out what is the probability that these two will belongs to negative. So for negative sample, it is 1 minus positive sample, which is nothing but negation of C neg into W. So this is a mathematical representation, and this means you just try to train this one so that it will arrive as vectors which maximize these two probability. That the positive class, if you are selecting positive and W from this positive sample, this one will be maximum. If you are selecting negative and W, it will also need to be maximum. So for that, what will be my loss function? So this will be my loss function. So here is similar loss function. So minus log P, probability of positive given these two values, two vectors, C pose and W. And as for each positive, there are k negative. So I have k such probabilities. Just add them. Okay, and this will be my loss function, and use this loss function to train the model. Okay, so these two loss function will be used to train the model, and when you solve it, you will get this one. Okay, because this positive probability of this is nothing but sigmoid of C plus W. Here also probability means sigmoid of C minus neg I and W. Okay, so you just train through stochastic gradient descent. Stochastic gradient descent means so you take one by one, now update the parameters, and the when the training process completes, you will have the trained model. Okay, how to update the embedding? Very simple, because there are three what vectors, and one is C POS, C neg, and W. So you calculate, because they are the weights. So just calculate partial derivative of loss with respect to positive, partial derivative of loss with respect to negative, and partial derivative of loss with respect to W. And these are the derivatives, and use this derivative to update the weights. How will update? New CPOS equal to old CPOS minus alpha into this derivative. Similarly, for CNEG, new CNEG. CNEG is representing what? Negative context embedding. This is positive context embedding. W is original context embedding, means the target embedding. So these embedding vectors will be updated by using this updation rule of stochastic gradient, by using these derivatives. Okay. So you need k plus 1 updates in context embedding, whereas only one update in W, because there are k plus 1, sorry, k number of negatives, so that is they need to be updated k plus 1 times, and here only one, so it will be 1. So after every update, you will have different vectors. And what is the hyperparameter here? K is the hyperparameter. How many negative sample for each positive sample you have to take? It is for large database, it is 2 to 5, and for small database, it can be 5 to 20. This is up to you what but these are the recommended values. Okay, And how will sample it? You need to sample not just like this directly. You cannot sample count of w divided by count of wi. Rather, you put alpha to the power alpha. So what these alpha? These alpha generally a constant which is nothing but 0.75. So in this way you can sample. Okay. So this will increase the probability of sampling of a rare word and decrease the probability of sampling common word. So common word need not be sampled frequently. The rare word need to be sampled frequently. Okay. So hyperparameter, again the context window is also hyperparameter. Here I have taken two, that you can take also more than two. If you take narrower window, it will capture similarity better. But if you take wider window, bigger window, it will capture relatedness bit better. So that is a trade-off you have to do. Okay. Now, once the training is complete, you will have a matrix W, means trained W matrix and a trained C matrix. Generally, what we do, we just discard this C matrix and we take the target word embedding matrix as the final vector. Because you see, after every updation, every row represents the embedding of one word. As there are V number of words present, so for every word, D dimensional vector is there. So after the training is complete, you discard this, you take this embedding. So for every row, one word embedding is available. Sometimes what people are doing, instead of discarding C, they just add the two vectors and take the final vector as the context embedding. So you can take that also. Okay. Now the question is here. So how? So this is your once it is done, you got the word vector. This is called your word to vec representation for every word, and you can use this for further processing. Okay. Now question is how will use that? So there are three ways to use word to vec embedding in your downstream task. Let's say it's a classification task. You have text. So what you need? First you need to pre-process the text, means clean it. Then you need to create a word embedding. So let's say I have chosen to use word to vec. Now the question is how will you use that? So one is use pre-trained word vectors as model inputs and keep the vector fixed during training. What you do, once you there are some pre-trained word embeddings available already. These word embeddings are trained on some big corpus and they are available, their embedding matrix is available with the words. You just use them in your downstream task. This is one, without further changing them. Another way is that you just use the same scenario as one, but here tune the word with your model. Okay, tune means don't use the fixed word representation which is already pre-trained for in some other corpus. You use that, but you just do a fine tune on your data set. Okay, and during training that will happen automatically. Another is another is directly you can create what? A third one here I have not mentioned. Third one is you use some of your data, means you take some corpus, train your own word embedding and use that word embedding in the further downstream task. Okay, there are two or three options. So at the beginning of the model, let's say ball and bat may be close to each other. After end of the model, the ball and bat may be dissimilar, means they will be far apart. Okay. And the third one is train word embedding from scratch alongside the model. That what I have told you, that you just create a new embedding, not don't use the pre-trained embedding, rather create new embedding on your data set and use it. Okay. So embeddings here when I say that train word embedding from scratch alongside the model, that means it will be optimized for model metric if it is a classification accuracy rather than similarity. It can be considered if there is enough data or domain is specific. So that means if you have enough data, then you can use the third one, means from scratch you train your word embedding and use that word embedding for further solving your task. Is it okay? So this completes the word to vec representation. We'll have to do one demo. How we'll use that. Is there any question? Anyone has any question? Okay. So one thing it is very clear. that we don't have to write programs from the scratch. There are libraries available, and we can use all these three approaches to solve our problem using what to wait, and we'll see that. Okay, so let's see. There's no question. Anyone has any question on this part? Yes. Okay. So I think there is no question. So let's go to the demo part. Okay. So let's use word to bake and do a classification. Use it in a classification problem. Okay. So for that, you just remember there is a good library present for implementing word to bake is called Gensim. GENSIM. So first, what you do? Let's connect it. Just a minute. So Gensim is the library what we are going to use, because in Gensim the problem the what to make is properly implemented, and we can use all three ways. Okay, you can use a pre-trained model, we can fine tune the pre-trained model along with my data set, or you can also create from scratch. Okay, I will show you both of them, three of them. Okay, so first you need to install the Gensim. So very simple, pip install hyphen u gensim 4.x. So just you use this one. Okay, then what we need to do is just import these libraries, import collection, matplotlib for plotting, numpy, pandas, spacey, tensorflow, and all these scikit-learn pca, all these things you need to import. Let's see. Okay. Now, what happens now? We have imported all the necessary libraries, and we'll see which one will be used. What? Don't worry. So first, what we do, we use the pre-trained third-party vectors. Means pre-trained means already the what to vec is already trained on a corpus, and the vector, that W matrix is given, and we have to use that. Okay, so we call it as pre-trained. We don't have to train from the scratch. And let's say there is a different what to vec models are available on pre-trained models. One good model is a Google News corpus, means a what to bake model with 300 dimension, and it is trained on 3 billion words from a Google News corpus. Okay, and let's download it. Download that corpus, because it is more than 1.5 GB of data. Okay, now it is downloaded. Put this file, that is Google News vector hyphen negative 300 bin gz, into a embedding file. So now this is my embedding vector which I have downloaded, because these vectors contain pre-trained word embeddings. Okay, so first thing what we'll do, so we cannot use all the vectors because it's a very big embedding vectors. Sorry, big matrix. So what we'll do, we'll only use 200,000 of them. So for that, the keyed vectors dot load what to vec dot format from the embedding file. Binary is true, limit is 200,000, and this is just downloaded. and that downloaded file will be available in word underscore vector. Okay, now word underscore vector contains words from these news corpus and their corresponding vectors, and we can use many different what methods of these word underscore vectors using that, so to calculate similarity and other tasks. So let's see, now the vectors is ready. So let's say I want to find out what is the word vector representation for pizza. So to do that, what we'll do, because word vectors contains all the words and their corresponding vectors, so you just call word underscore vector, and within square bracket write pizza. So and that will be given to pizza as the variable. You just print it, pizza dot shape, and pizza, you see this is 300 dimension vector. So just to see here, vector dimension is what, 300, because I'm asking pizza dot shape. So there is a 300 dimensional vector, means every word has 300 values. The vector size is 300, and these are the values. Okay, because these values we have not trained already, it is trained on the news corpus and we just use it. Okay, now if you want to find out similarity between two words, so there is a similarity method available. So just call word vectors dot similarity, pass two words, for which two word you want to find out the similarity score. It will give you the dot product of these two vectors, pizza and tomato. Here pizza and sauce, pizza and cheese. If you run it, you will see there is some kind of similarity. 30.35 is similarity between pizza and tomato, 0.36 is between pizza and sauce, pizza and cheese is a little bit higher similarity, 0.47. Okay, so and let's see which are not similar. We know pizza and gorilla, pizza and tree, pizza and yoga, they are not similar. Let's see what is their similarity score. So same, just call the similarity method, pass these two, and you will see the similarity score is only 0.10. This is 0.11 between pizza and a tree. Between pizza and yoga, it is 0.14. So that means they are much more similar. Pizza and tomato are much more similar than pizza and gorilla, because the similarity is very small. Okay. Now question is, what about out of word vocabulary? Because you see what we have done, we have downloaded the word vector representation which is pre-trained on Google corpus, and it has many words and their corresponding vectors. For example, you give a word and that word is not available in that word corpus, sorry, in that word vector, so you cannot get the vector, so it will throw you error. So now you see, if I want to find out what is the word vector of Wimbledon, because Wimbledon is never appearing in the Google corpus, so for that you cannot get any vector. So we call this as out of vector, and for out of vector there is no way to deal with that. It will give you an error. You see, it is say key Wimbledon not present. Okay, there is another method present called n underscore similarity. It will show that between two set of words whether they are similar or not. So let's say I have dog bites man, canine nips human. So because we know that the n similarity generally takes a list of words, so instead of giving the sentence like this, you have to split it into a list of words. So when I do dot split, so it will create a list of word for this list will contain dog bites man, canine nips human. Dot split, it will also create another list which will contain canine, nip and human. Okay, now you just pass to word vectors dot n underscore similarity method. So it will try to find out the similarity score between two set of lists. So see, it is 0.53, means they are quite similar. Okay, the similarity score is higher. But you imagine these two, if you represent them through bag of word or one hot encoding, so their representation will be zero. The similarity score will become zero, because both of them do not have same number of words or same words. Okay. Similarly, let's say I want to find out Martin dolphin are hostile. I flunked calligraphy school. Is there any similarity? So yes, the similarity is very small. That is 0.14. Okay, because these and it's also quite simple to note that here this Martin dolphins are hostile and I flunked calligraphy school. They are totally different things. Okay. Similarly, here you also calculate dog bites man, man bites dog. Now it will give you similarity as 1. Now you see, this is the problem what we need to deal with when we will go for other contextual embeddings. Because you see, in word to vec, it gives dog bites man, man bites dog. They are totally perfectly similar. Because why it is giving that? Because their meaning is somehow it is capturing some kind of meaning, because they are not capturing the meaning of the whole sentence. It's just capturing the meaning of the words. That's why it is giving 1. And it does not capture the word order, because if they can capture the word order, then the similarity will be different. It should not be 1, because as it cannot capture the word order, that's why the similarity is 1. Okay, so that is a problem with what to make, that we will discuss in future. Okay, similarly, if S1 is this one, Volkswagen intends to double electric car sales in China. First, Toyota with solid state battery will be hybrid. So if you want to find out this n similarity, it is giving 0.52, because both sentence is related. Okay, they are talking about cars. Okay, now there is another method which will give you the most similar other words for a given word. So let's say word vectors dot most similar. If you take positive as a cell, top n is a 10, means I want to find out top 10 words which are close to cell, or which are more similar to the word cell. If you run it, you will see it will give you cells with a 0.81 as similarity score, cells 0.61, cellular, tumor cells, means it's talking about the biological cells, uh, proteins, molecules, so they are similar with cell. But if you use cell with phone and find out top 10 similar words using most similar, it will give you telephone, phone, cells, cordless phone. So they are similars. They are it now. It is not talking about biological cell. Okay, that means it is capturing somehow. It capturing some kind of meaning. Okay. Similarly, there is a method which will give you which do not match in a list of words. So here the method is called does not underscore match. So does not underscore match, if you pass a list of words, let's say apple, orange, hamburger, banana, kiwi. So you run it, it will show that hamburger is not related to all others. So because it captures the relationship, find out the similarity score, and this the hamburger similarity with other words are very small. That's why it is left out. It means it does not match. Similarly, if Microsoft, Apple, Toyota, Amazon, Netflix, Google, if you put this does not match, it will say Toyota, because all others are somehow related, because they are means computer companies or software companies. Toyota is a manufacturing the car. Okay, so now these are the different methods which are already available within the GenSim vectors, which you can use to calculate the similarity, which are does not similar, find out top 10 similar words for a given word, etc. Okay, now let's do one thing. Let's plot it. Some of the words which we have displayed, which we have discussed in our slides, that swim, swimming, cat, dog, feline, road, car, bus. Let's find out their word vector representation and plot them in a 2D in a 2D space. So as the each words vector representation is 300 dimensional, so it is not possible to create a image or visualization for a 300 dimensional. What we can do, we can convert them, this 300 dimensional vector, to a 2 dimensional vector. How to do that? There is a algorithm available that is called a PCA, principal component analysis. The algorithm you don't have to write, already it is implemented. You just call it, pass the vectors, it will quash the vector to a 2D vector. Okay, so now this is the function what I have used, that it will take the model and words, it will take the words one by one and transform them with the PCA. So PCA is called fit transform word vectors. So only how much? Not 2. So let's do it. And I am calling the PCA and pass these word vectors. And see, this is the vector representation. Now you see, swimming is very close to each other. Cat, feline is close. Dog is also in that same group. Car, road, and bus, they are also close to each other. Means they are in another group. So that means our what to make representation captures similarity very well. Okay. Now let's see, there is another concept which is very familiar or very important in finding out the this kind of relationship. For example, let's say you want to solve some kind of analogy, word analogy. Let's say Rome is to Italy as London is to dash. So Rome is to Italy means Rome is capital of Italy or is a city of Italy. London is also a city of UK or United Kingdom. Okay, so how will you calculate that? So very simple. That means Rome minus Italy equal to London minus, if you find out the vector. So if you do this calculation, Italy plus Rome, sorry, Italy plus London minus Rome, it will give you that what word is close to this vector. So what I am doing, I am finding the vector of Italy, adding the vector of Italy to a vector of London, and subtracting that vector from the vector of Rome is subtracted from that addition. So whatever vector you will get, that is, you see, that is close to this UK or United Kingdom. If you do that, this one is doing that. So you see, it will give you UK, Britain, or United Kingdom. So this analogy kind of solution problem you can solve using this. Okay. Now also you can print this. Now you see Britain, UK, Rome, and Italy. Okay, because you see Rome to Italy, the distance is same as London to Britain or London to UK. That means London minus UK equal to Rome minus Italy. So you can solve it. If anything is not given, you can do the addition, multiplication, sorry, subtraction, and get other vectors. Okay. Now the basic thing is over. So what we'll do now? We will create a classification using this word vector. What to make? Okay. So first thing first, we'll download a data set. Let's say I am going to download a Yelp review dataset. Yelp review means a movie review dataset. So just download that Yelp review dataset. Okay, just load the what to bake model. First, you load the what to bake model because you have the embedding file already you have downloaded. And here I am increasing the size as 1 million. Okay, so it is 1 million vectors we have downloaded. Now what we'll do, we'll use Yelp review. So first, download the Yelp review dataset. This Yelp review dataset contains sentences and the review, whether it is positive or negative. Okay, and here the instead of positive negative, it is giving the value as 1 and 2. So let's see. So unzip it, unzipping that review which I have downloaded. Okay, now that contains a train and a test. So first, what we'll do, we have to read that file. What is that file? Here you see in the data set, in folder you see Yelp review. Under this there is a train .csv file which contain all training data, and test.csv file which contain the test data. So we'll use this train.csv to train our model and test.csv to test our model. Okay, so let's see. First you load this train.csv with pd with your pandas data frame and give their heading name as sentiment and review. Okay, now if you see this shape, just a minute. So it has 55,60,000 rows and 2 columns. First column is sentiment, second column is review. Review is your positive or negative. So if you see some of the first five reviews, so this is the review, this is the sentiment. The sentiment is not positive, negative, it is represented by numbers 1 and 2. Okay, so 1 is positive, 2 is negative. Okay, so in our model we are not going to use all 5,60,000 because it will be very huge. So let's restrict. So select only some of these reviews. Let's say I want to select only 100,000. So I am putting train size at 100,000. Sample means randomly sample from the Yelp train. So just copy it. So we'll have 100,000 rows with 2 columns. Okay. Now, next thing is that the sentiment values are either 1 or 2, but we have to convert them into 0 and 1. Why? Because we have to use a classification model where the last layer will be sigmoid, and the sigmoid value is between 0 and 1. That means we need to convert them into 0 and 1. So how we'll do that? Now just use the replace method to replace 1 with 0, 2 with 1. Okay, just don't do that. So it has been done. So some warning is showing. So now you see the head. Previously it was previously it was 1 and 2. Now this is replaced by 1 and 0. Okay. So now you do the train test split to split the training data into training and validation. Testing is different. So from the training data, we segregate some 85% will be used for training, and during training 15% will be used for validation. So just use the train test split function to do that. And once you have done that, now what you do? You just take the review into train X or train, and Y train make it as sentiment. Similarly for validation also same thing. Means segregate X and Y. So means sentence in one data frame and is sentiment in another data frame. Okay. So now my data set is ready. What is my data set? I have collected Yelp review data set with 100,000 data with 2 columns. One column contains review, second column contains sentiment. What I have done, I have segregated into 2 portions. 85% of this training data will be used for training, 15% will be used for testing. Now for this, once you have segregated, next job is to segregate the feature and the label. So label is sentiment, feature is review. So we have segregated it into 2 different variables. One will contain the features or that the sentence, another one will contain the sentiment. Once it is done, first thing for before creating model is to create a tokenizer. Tokenizer's job is to, we already discussed in the last session, tokenizer's job is to tokenize it, pre-process it, and create a vocabulary of the words. Okay, and give indexes. Means these value will be used. Means that vocabulary's index will be used as the index for the or the vector for the every sentence. So there is a keras tokenizer already available. You can use spaces tokenizer like we have used. So here I am not using that. You can do that. Just I am using the keras available tokenizer. Just I have used, these are the filters. Means filter the numbers, these special symbols, and make lower as a true. Simple pre-processing technique. And the number of words is 200,000. Means just create a vector with most words which belongs to 200,000. Means rest you just discard. So my vocabulary size will be 200,000. Sorry, 20,000, not 200,000, 20,000. Okay. Now fit it on my training review. So just fit it using fit on text. So my vector will be created. Sorry, my yes, the vector is created. Now if you want to see, now you see when I say fit on text, actually the vocabulary is created. Now once the vocabulary with index is created, now we have to convert every sentence, every review with their index values. So for that, there is a method available called text to sequence. Text to sequence job is that the sentence contains words and it will be converted to index of these words in the vocabulary which we have created. So just use that. And if you want to see, it will take little time. Now if you want to see first sentence, so first sentence is extend 0. Now you'll see it will not have the sentence, the words, rather the words with their corresponding indexes. Now this is the index of the words from the vocabulary for the extend. Okay. And if you want to see what is my first 3 words, so from in the vocabulary the index is 49. So that's why 49 is replaced by for the from, and my is 14, hospital is 2224. Okay. So what you have done, create a tokenizer which will create vocabulary with their indexes, and then call the text to sequence method which will convert every sentence to its corresponding token indexes. Okay. Now these token indexes need to be converted into vectors. Okay. So I will do that. Now if you want to create reconstruct it, means from this number to sentence, you can use sequence to text. So if you use sequence to text, it will convert number to sentences. Okay. So let's see. Okay, now what we'll do, this is also not required for the completeness we are doing, that for every sentence the length of the words may be vary. One sentence may have 20 words, another sentence may have 10 words. So for that we need to pad the sentence. We call is as padding. Padding is not required for this task, but some other task in future when we will do the RNN, so in that case we need padding. So for its completeness we will see how the padding will be done. What padding is doing, now you have to give a maximum length. So if a sentence is more than that length, it will be truncated. If a sentence is less than that length, it will be padded with zeros. Okay. So let's say my max length I have taken as 200. So when I call keras.preprocessing.sequence.pad sequence on the X train and max length is 200, so what will happen? Now in X train, whatever sentence, it will check each sentence or each row, and if the length of the row is less than 200, so it will add that many zero to make it 200. If its length is more than 200, it will remove some of the portions and only 200 first 200 words will be remaining. Okay, so let's run it. So now pad sequence is done. Now if you see zero and past means first and second sentence. Let's see first and second sentence. Now first sentence is started from here, end here, isn't it? So, but you see this is my first sentence. 200 values are there. Means these are the word index. But as this first sentence contains more than 200 words, so it is truncated. Rest are means discarded. But for second sentence, train one, you see it is less than 200. That's why the zeros are padded. Okay, so make it 200. So now once the padding is done, every sentence in my corpus has a length 200. Okay, so next what we do, we just convert text to sequence for validation. Same thing will be done for validation as we have done for training. Okay. So if you want to see tokenizer word index of good, you'll see this is the 34. Good is a word index of 34. And for first 50 word vector, this is the word vectors for good. Okay. Now it is done. So now next job is that as my word vectors are ready, sorry, my index is ready for every sentence, means every sentence is converted to its index, but we need to convert each index into its word vectors. That means as already we have stored the word vectors in our word to vec model or word underscore vector variable, just copy the corresponding words into these indexes. How will do that? Now this is going to do that. First, what are the number of tokens? Now it is tokenizer dot word index plus one, because obviously it is start with zero. That's why we do a plus one. And what will the embedding dimension? It is 300. So first create a 300 dimensional vector with all values 0 for every index. Now what you do, you run through or you just go through each word vector from the downloaded word to vec, and if you see if it is available, then copy it. So that will copy means convert every word to its corresponding word vector which we have downloaded. Okay. Now if you see what is the index of good, now you see this is the word vector. Now the indexes are converted to vectors. Okay. Next is to create first layer of the model, that is called embedding layer. So here is the twist. As the embedding layer is already there, what you do here, either you can make the embedding as it is, means without changing it, or you can fine tune it with your data set. So for embedding layer, layers.embedding, what is the number of tokens? Number of tokens already there in norm underscore token. Embedding dimension is 300 is already there. You just initialize them with embedding matrix. Okay, because embedding matrix is already created, you just initialize them. Input length will be max length, that is your 200. Trainable equal to true. You remember this one. Trainable equal to true means whatever word vectors we have downloaded from the pre-trained model, that will be fine-tuned on my corpus, because trainable is true. If you make trainable equal to false, it is not going to train. Rather, whatever it is trained, that will be used in the downstream task. Okay, so here I am making trainable equal to true. That means the second option means during training it will be fine-tuned. Okay, now very simple. Now you create the model. First is keras.sequential. That sequential API is used. So now you see here I am using a different approach. Previously within the keras sequential we have used a list and add all the layers. Now you can also do like that also. Just create a model object and just add model.add. So call model.add, pass the embedding layer. So embedding layer will be added. Next layer will be global average pooling 1D. Why we need this? You see the embedding layer, when we do, let's say you have a sentence with 10 words. For every word we have a 300 dimensional vector, but your model cannot take 300 300 dimensional vector. It cannot take, it can only take one 300 dimensional vector. So what I have to do, I have to convert these 10 300 dimensional vector into one 300 dimensional vector. How? By taking the average. So that will automatically done by this layer called global average pooling 1D. So global average pooling 1D, what it will do, it will take all the word vector of the sentence, because let's say a sentence has 15 words, so every word has these corresponding 300 dimensional word vector. It will take all these 15 300 dimensional word vector and take the average to make only one single 300 dimensional vector, and that can be taken as input by the layers, other dense layers. So that's why we use global average pooling 1D. Next layer is dense layer. I have passed 128, activation is ReLU. Another dense layer I have used 64, activation is ReLU. And the last layer, as it is a classification either 0 or 1, so the dense layer is 1, activation is sigmoid. Same. And next, once the model is ready, next we have to call the compile. We have passed the optimizer as Adam. As it is a binary classification problem, so the loss will be binary cross entropy. If it was a multi-class classification problem, it should have categorical cross entropy. And metric I have used accuracy. Okay, just create the model, compile it. This one I'm not discussing now. What next is fitting, train the model. Now call the fit method on the model, pass the xtrain ytrain, and I'm going to train it for 20 epochs. Okay, and batch size is 512. Validation data is already there. So just train it. So it will take little time. Is there any doubt till now?
Have you run all the previous models which I shared with you? All the previous model Sarah has already shared with you. Have you tried all those things? Those who are attending the classes today. Anurag, have you tried?
Yes, sir.
Okay, good.
Because without if you do not do by yourself, it will be difficult to grasp many things. Okay, so you see here, so we are running it now. See, the loss is decreasing. Okay, for the training loss, after some time the validation loss is also in decreasing, then it is increasing, means it is clearly overfitting. Now see here 93, but it becomes 84. Here accuracy is 93, it is 92. Up to this it is okay, but after that it is again fluctuating. Okay, so let's plot it, then it will be easier to understand. Let's plot that validation accuracy with training accuracy. Just plot it. Now you see here the training accuracy is decreasing, but the validation accuracy is fluctuating. That means it is going, means clearly it is overfitting. Up to let's say 4 or 5, up to this it is okay. Means how many epochs? 1 2 3 4 5 6 7, up to 7 epochs it is okay, then it is fluctuating. Okay, similarly the accuracy is also same, the loss and the accuracy is also same. Okay, so now what we'll do, so we can create another model where we'll stop before it is deviating. Okay, so same thing here, trainable is true, same model. Okay, so just I am training it only for 3 epochs. Okay, instead of for 20 epochs, let's train it for 3 epochs. You can also train for 7 epochs also. Otherwise you can use early stopping callback, like we have discussed. That is best way to do that, instead of first training, the first you train a model, then observe, then train another similar model with a less number of epochs. It is time consuming. You can use directly early stopping. Okay, so now my model is ready. Let's say my model is ready. Okay, now what we'll do, we'll test it on test data. So load the test data, because test data yet we have not loaded. So just load the test data, do all the same kind of pre-processing what you have done on the training. Okay, then convert them into one and zeros. Okay, then pre-process it. Once it is done, then evaluate. So your model is ready. Now evaluate on the test data. So on the test data, it is giving me 84% as the accuracy, and 0.3939% is the loss or error. Okay, so if I got a new review, how I will use this model to infer or to give the prediction. So for that, I have created a simple function. It will take the review, new review, it will tokenize it. The tokenizer will be used to convert this text to sequence, means convert it into numbers, then use the pre-process, pad it so that 200, the dimension will be 200, then predict. Okay, so this method is there, and I have taken two reviews. One is the best fast positive review, that is the best seafood joint in East Village, San Diego. So this review is positive, and this review is negative. That we know. Let's see whether my model can predict it correctly or not. So I am passing these two reviews to the sentiment function. Now you see, first one is 99.9, means 99% it is positive, and it is 0.08, means 8% it is positive. That means it is negative. So it is correctly predicting. Okay. So this is one way you can do. Means you use trainable equal to true. Another way is that don't use pre-trained model, pre-trained word embedding model. Directly you train your model with the existing data set what you have used. From this data set it will create the vectors and use that vector directly. Okay, so for that what we'll do, for the embedding layer, just use input dimension equal to dimension. Here I have not used any pre-trained word embedding, just directly I am using the layer, and with trainable equal to true, because by default trainable equal to true, I am not using any pre-trained model, and directly other things are same. And let's run it. Previously, in previous case, the layer embedding layer uses pre-trained word vector. Here I am not using any pre-trained word vector, rather whatever corpus I have, from that corpus it will learn the word vector and use it in the classification. Okay, that we are doing. Okay, so this is this. Now if you evaluate on the test set, it is giving me 83, and that is not that much improved. So same, it also previously it is giving how much, 84, now it is giving 83. So word vector here is good. Okay, now third one you have to try. So what you have to do, you just initialize the embedding layer. Okay, but here don't train it, means make trainable equal to false. Rest you create some model and fit it and find the value for the test set. This is your task to do. Okay, besides the word to vec as a static embedding, other embedding techniques are available. One is called glove, that is global vector for word representation. Another one is doc to vec, and the third one is fast text. So this fast text is a little bit better. Why? Because it uses subword embedding. It means subword tokenization. It's not tokenizing by words, rather it is tokenizing subwords. So there are also other subword based tokenizer available. Your LLMs are using this subword based tokenizer, and the most important subword based tokenizer which almost all LLMs is using, that is called BPE, byte pair encoding. If time permits, also we'll discuss that. Okay. So if you have interest, you can go through these websites where the information you can find for Glovi, Doc2Vec, and Fast Text. Okay. Is there any doubt? So everybody please try this exercise. Okay. Same, you use your own model. I have used 3 layers. You can increase it, decrease it. You can use early stopping. You can use also dropout to overcome this overfitting problem. Early stopping is one way, dropout is another way. You can use a dropout layer like already we have discussed. So try it. Okay. Any question?
Yes, any questions? Swaroop, Swaroop, have you implemented all this? Okay. Okay then.
Okay.
Should stop here.